Okay, so where are we now? We are in the second module talking about neural networks and how we can optimize neural networks to make them more efficient, regardless of what hardware they're going to run on. So the first thing we talked about is quantization, how to use a smaller number of bits, a lower number of bits to represent numbers in a neural network. And we saw that you can do that quite effectively without losing any accuracy. The next thing we talked about was pruning. So we talked about how to remove superfluous parameters or channels or pieces of the weight tensor, basically, to reduce the number of computations that you actually need to do and remove anything that's going to be multiplied by a very small number or by zero. So that's what we call ineffectual operations. And so we're going to talk about another method that also shrinks neural networks called knowledge distillation today. So this is actually quite a fun one because it's different from the other ones, which looks for redundancy within a model. This one is a method to transfer kind of expert knowledge from a large neural network to a small neural network. And the analogy I like to give there is that you're all students. Imagine if you came to the lecture and instead of me kind of standing here making slides and pointing to things, I just give you a bunch of books, put them on your desk, and ask you to learn. So would that be effective? So typically not, unless you're really good at navigating books. And so instead, what we do, we put this thing in the middle called a teacher. And so the teacher absorbs all the knowledge in those books or all the data in those books, and then transfers and distills that data down to something that, let's call it knowledge. And the teacher then attempts to transfer that knowledge onto the student. And that's basically the concept of knowledge distillation. By the way, by a show of hands, how many people already know what knowledge distillation is? 3? Okay, good. And so we will also not kind of withhold that data and the raw material from the student. We will also give them the books to kind of augment their experience. And that's why you guys have the weekly readings and all of those book chapters to go through by yourselves. So I'm doing lecture, but also you have to go and read the actual material, right? Because as we will see, the knowledge coming from the teacher is sometimes noisy and sometimes even incorrect. Whereas the knowledge from the books, we assume that it's 100% correct. And so that's something to keep in mind. So what does this mean for a neural network? So I'm talking about teachers and students and people. For a neural network, the teacher is typically a large neural network that has a very good accuracy, right? So in the field of vision and image classification, this would be like distilling knowledge from a huge network like ResNet 101 to a mobile net, for example. And this example is a bit dated, but let's go with it. And the key thing here is that larger neural networks are actually easier to train, whereas smaller neural networks are much harder to train, but easier to deploy, obviously, as we know. And so we want to train a large neural network, but deploy a small neural network. And knowledge distillation is one way to convey that training information or training usefulness to the small neural network. So it was proposed in 2006 in a very kind of simple formulation by Karuna et al. And then it was generalized and kind of the term was coined in 2015 by Jeff Hinton, I think after he joined Google. I may be mistaken, but I actually think the Hinton paper was never, I think it was never accepted at a conference and he just put it on archive. Now it's like cited 100 million times, but I think I may be mistaken there. So that's what we do. As you see the diagram on the right here now changed, the knowledge is not books, now it's this training data. So we use the training data to train a large neural network, and then we have this process whereby we transfer the knowledge from that large neural network to the small neural network. And what is that knowledge? In one case, as we will see, is going to be the softmax class probabilities. So the output of the large neural network, essentially, in the case of image classification. So in this lecture, we'll try to cover these 3 items. So we want to kind of understand what knowledge distillation is, and we'll go into some detail of how it works and why it's needed. So hopefully for the 3 people who already know what this is, this won't be too boring. Then we'll do a short exercise where you write some PyTorch code to perform knowledge distillation. And then finally, we'll look at some advanced knowledge distillation techniques and open problems in that area. And so, so if we roll back to kind of your first lecture of your first class on neural networks, it looked something like this. You know, you have an input. Again, we're taking image classification as an example throughout this lecture, but this can be applicable to other domains and other problems as well. So we have an image at the input. Let me do this. So you have an image at the input here, and then you have a neural network, which has the standard, you know, input layer, hidden layer, and output layer. The output of a classification neural network is typically called logits. And so we basically transform those logits into probabilities or class probabilities by putting them through a softmax layer. Then we have a loss function, which takes on the other end these targets or the ground truth. So for example, this image, we know it has a cat. When you see it, you say this is a cat. And so we put a 1 where a cat is, and we try to train this neural network through backpropagation by showing it this ground truth and minimizing the error function between the ground truth and the output class probabilities there. So the key observation here is that these hard targets, what we're calling hard targets or ground truth, they have only information about the correct answer, right? So it has a 1 here and a 0 everywhere else, right? But we're not teaching we're not conveying any information about the wrong classes. So for example, if you were to mistake this for something else out of those classes, I mean, how many of you would mistake it for a boat, for example? Like it's very unlikely, right? But maybe someone could mistake it for a dog. It's possible. Or if there were different kinds of cats, like a puma or a lynx or something, maybe you can mistake it for one of those. So we want to provide something called soft targets, which not only convey information about the correct class, but also give you some information about the incorrect classes as well. So I want to say this is definitely not a boat. This is definitely not a bus. It may be a dog if you're looking at it from a certain angle. You know, if you make that mistake, you're fine because you've already identified many correct features like eyes, nose, mouth, ears, you know, furry texture. These things are common to cats and dogs. So you already did half the job there, right? But, you know, you don't have these things on these other classes. So where do we get those soft targets from? Yeah, so an example of soft targets here would have kind of near 0 probability everywhere except for cats and dogs. But where do we get them from, right? That's the current question. So what do people think? Who thinks it's number 1, kind of from labeling some data and trying to cluster similar classes together and using kind of the distance between those clusters or something like that? Who thinks it's number 1? Could be, okay. How about 2, using an equation? A very interesting, what's the equation? Yeah, that's also my question. Oh yeah, maybe no one will choose number 2. Yeah. Yeah, that would be kind of a specific case of number 1. But yeah, it's yeah, I mean, you're right. So it could be, there could be an equation. Who thinks it's number 3 from a trained neural network? Okay, most people. And who thinks it's number 4, using kind of annotation and labeling? So yeah. Yeah, I mean, it could come from expert annotation, but I mean, it wouldn't be too dissimilar from hard targets, right? Because they're currently manually labeled as well. So it could come from expert annotation as well. I mean, for the purpose of knowledge distillation and how people do it in practice today, it's like most of you guessed, right? So we're using a trained neural network the output of a trained neural network as the teacher. So we're using that as the way to get these soft targets. And so this is what it looks like. So we have the same image. It goes through a small neural network and a large neural network. And here we're only training the small neural network, right? We output the logits, we put it through a softmax function, and the output of the large neural network, which we know has kind of good accuracy, we call these soft targets, right? And in this case of a cat, it already kind of has this interesting information where, you know, well, I'm not labeling the classes here, but this was dog and this was cat. It already kind of has it assigns some probability to similar classes. This is one of the characteristics of neural networks, because it kind of goes hierarchically through different features that you have in the images. Then naturally it would also kind of assign some probability to wrong classes which share many of the features of the correct class, right? And so we would put this into the loss function. In the most simple case, the teacher network is already pre-trained, and we would do backpropagation only to the small neural network. So basically, the large neural network here is part of the loss function. It's a way to get these soft targets, and then we do backpropagation normally to train the small neural network. And so, so the images used in this kind of scheme are usually called a transfer set. Typically, it's a subset of the training data. It could be the whole training data, and it could be done during training. But in a specific case, it would be called the transfer set. And then the question now becomes, what is the loss function that we're using here? So, so before even talking about the loss function, let's talk about the softmax function. So the standard softmax function, if you recall, looks something like this. So the output is equal to exponent of the logit divided by the sum of the exponent of all the logits. So that's a softmax function which gives you probabilities from 0 to 1 out of these logits z, denoted by z here. And so what people usually do is that they add this softmax temperature. And this is kind of a new hyperparameter that's especially useful for knowledge distillation. So the example I'm showing here is a bunch of logits, Z, and a bunch of softmax probabilities with different temperatures. So we will see, you know, if you look at the highest value logit, 3.7, with the temperature equal to 1, it would have probability of 0.8. With the temperature equal to 10, so the higher the temperature, the smoother kind of the probability distribution. So it will have kind of a probability of 0.276. So the ranking between the different classes here still stays the same. This one is still the highest probability out of all of them, and this one is still the lowest probability out of all of them. But basically, we are magnifying the values for the wrong probabilities. And remember, in knowledge distillation, we're trying to get more information about the wrong classes. And so just numerically, for this to be effective, this softmax temperature turned out to be something actually quite important. So in Hinton's paper, he calls it dark knowledge. So this additional hyperparameter, the higher your temperature, the more dark knowledge it exposes. But basically, what that means is that it just magnifies the values for the wrong classes. So, and makes the distribution a bit smoother. Okay, so back to this diagram now. So we have a softmax with some temperature. And this is a hyperparameter, so there is no real kind of correct value, but I've seen temperature in the range of 5 to 10 being used a lot. And then I still have kind of many questions here. Why do we even use the softmax? Can we just use the logits instead of the softmax class probabilities, right? And the answer is yes, we can. I think even the original paper did that. They didn't do the output of the softmax function. So you can use the logits, they still convey kind of the same information. It's just, I think, numerically less nice. And then what is the loss function? So can someone tell me that? So usually we use like cross entropy loss to train kind of a classification neural network. Here, we don't have classes here. We don't have kind of ones and zeros, but we have a probability distribution, right? So what would the loss function be? Yeah, that's correct. So what James said is that we would still use kind of something like KL divergence, and that's exactly right. So we have two probability distributions. We want to quantify the difference between those two probability distributions, and the easiest way to do that is to use some kind of divergence, like KL divergence function, which can do that. And then, yeah, we already kind of talked about what temperature to use during training, but what temperature do we use during inference? So we trained this neural network using distillation with a temperature equal to 5 to expose all of this dark knowledge. But what do we use during inference? So what do you think? Same as training. So why would I use the same temperature as training, for example? So during training, I used it to expose kind of more information about the wrong classes. But during inference, do I still need that? When t equals 1. So yeah, so this is the correct answer. So I mean, any temperature other than 0 would give you the right answer, right? Or would give you the same answer, because that just smooths the probability distribution or makes it kind of more pointy and more concentrated around the right answer. But during inference, you don't have the reason to change t anymore, right? Like you don't want to expose this dark knowledge. You don't need to use it during training. And so what people usually do is that they just use the standard softmax temperature during inference. Some people, in some cases, we also rely on the probability numbers to kind of find confidence in the kind of the output, or quantify the confidence in the correct output versus the wrong outputs and so on. And so some people do rely on the value coming out with a softmax temperature equal to 1. And so typically during inference, there's no reason to change softmax temperature. It's only a training hyperparameter, basically. Okay, so far, this is what it looks like, right? We have a large neural network. We have the softmax with temperature. We have our soft targets coming out of that large neural network. We use a loss function like KL divergence to compute this what we'll call the distillation loss. But as I said at the beginning of the lecture, we still want to get the raw data and these books to the student somehow. So how do we do that? We can still train with the hard targets, right? So with the actual ground truth predictions from the labeled data itself. And so usually what happens there is that we have another output with a standard softmax temperature. We train it with the hard labels. So now here we have kind of a 1 where the correct class is. We don't have soft targets anymore. This is standard training. We have a loss function. Usually it's cross entropy loss, which is a specific case of a KL divergence for discrete labels. And then we call this the student loss. So we do normal training with the student loss, and then we also add this distillation loss. Yeah. Do you tune T the temperature, you mean? So it's like any other training hyperparameter. So you kind of, you binary search until you find a good value, or you do hyperparameter optimization. Usually we don't anneal. Do we anneal the softmax temperature? I don't think we typically change the softmax temperature during training, but it's something you can do as well. like learning rate or something, you can keep kind of adjusting how much of it, how big the magnitude of it during training. So so during neural network training, you have many hyperparameters, right? So so learning rate, for example, is one. The number of epochs even to train, the different data augmentations you use. So all of these things are kind of empirically tuned to get the best result out of training. And T is just one other parameter there. So so people tried the standard softmax temperature, they tried a higher softmax temperature, and empirically they found that higher temperatures typically work a bit better. And so I'm hesitant to kind of give um, any specific answer as to why we should search for a good t-value, except that empirically it works well. Like I said in the original paper, the reasoning is called, to expose more dark knowledge, obviously, and to kind of magnify the values of those strong classes. And so that's kind of just to get some intuition about it, but why does it actually work and what value is best? It's all empirically driven, I would say. No, you combine them and you do one backpropagation. So basically, I will show now how we combine them. It's quite straightforward. We add a plus sign between them, right? So so basically, your loss function now becomes, um, it consists of two parts, and maybe we can take a closer look at that. So the first part is the student loss, and this is the standard cross entropy loss, right? So you have a loss function, you have your hard targets y, you have the output of the softmax with the temperature equal to 1, with the logits zs, z student, and then plus another loss, which is the KL divergence in this case, can be any kind of distance metric between two distributions. And the two things it's comparing is the output of the teacher network with softmax temperature T, and the output of the student network with the same softmax temperature T. We call that distillation loss. And we just scale each of them using alpha and beta, basically. So it's a scaled, it's a weighted sum of the normal student loss trained with hard targets and the distillation loss trained with soft targets coming out of a teacher network, if that makes sense. Yeah. Yeah, that's correct. So we just introduced two more hyperparameters. Usually beta equals 1 minus alpha. So it could be just one extra hyperparameter. But yes, in totality, there are 3 hyperparameters here at most. So, and again, it's empirical. What works best values to start with is usually kind of 0.5, and then you kind of tune it. And there is no magic value for all neural networks where it works really well. There are some kind of rules of thumb, and then you go from there. So okay, so this is code to train a neural network normally, right? So what do we have here? We have a model. It's MobileNet v2. We have an optimizer. We have this training loop going over different epochs, and we have a training loop going over our training data. And then, the outputs equal to the outputs of the neural network, given those inputs. The loss is the cross entropy loss, and we compare it with the labels, and then we do backpropagation. So if I want to change this code so that now instead of doing this classical, training with labeled data, we want to use knowledge distillation. So what do I do? So first, you load the teacher network. So in this case, I loaded ResNet 101, like I said in the very early example. And I have those hyperparameters. Here I just have alpha, and I'm assuming that beta is equal to 1 minus alpha. So take a couple of minutes, try to write down the code that goes into that green box. Okay, let's go over the answer. So I mean, the standard one looked like this, right? Like we had just the output of the neural network. We have these labels coming from the annotated data. and we have one loss called cross entropy loss between the output of our model softmax and the labels. So now we have this extra network, the teacher network, right? And so, and we have this extra loss, distillation loss. So the first thing is, we do a forward pass with the teacher. So we get the output of the teacher, outputs T. We still compute the hard loss, which is the cross entropy loss between the outputs and the ground truth labels coming from our training data. But we also compute this distillation loss. And so how do we do that? First, we compute the softmax of our student and teacher output. And we include this temperature. So we divide by T, which is our softmax temperature here, right? So now we have P and Q, which is the output of the student network with softmax temperature T, and the output of the teacher network with softmax temperature T. We compute our extra loss called distillation loss. And this is, like we said, we can use the KL diversions for that to compute the difference between two probability distributions. So P and Q in this case. And then our loss function simply becomes a weighted sum between the hard loss or the student loss and the distillation loss. Any questions about this code? But I mean, basically, this is it. This is what distillation is. We add these 3 or 4 lines of code to our training loop, and usually it results in a bit of extra accuracy in your model. Tuning those hyperparameters is tricky, is what I found in practice. Applying this to different domains, we tried it with speech models at some point, is also tricky. Loss functions are a bit more complex there. But this is essentially the core idea and the core way to apply it in code. So, any questions? No? Okay. All right, so I mean, we just covered those first 2 learning objectives. And now we can chat a bit about kind of more advanced knowledge distillation techniques and open problems in this area. And so like everything else in machine learning, as soon as a new concept kind of comes out, people go crazy with it and they do kind of very interesting things. And so this is no exception. So the first thing we'll talk about is this teacher network. And so far I said it's a very accurate, large neural network that is easily trainable, but it doesn't have to be just one neural network. So often what people do is that they actually train ensembles of neural networks, which means multiple neural networks doing the same thing. And then they average their output to use it as an input to this distillation loss. And so what does this do? In general, ensembles or groups of neural networks, they can bump up your accuracy a bit. And so, but then it becomes very hard to deploy them, obviously, because they are, instead of having just one neural network, you have 3 or 10 in some cases. And so how can you deploy that on a mobile device or even on a desktop GPU? It's very hard. But to get the benefit of this extra accuracy, we can average their output and input it into the distillation loss. So this is one way to kind of do a fancy thing with the teacher network. So what are ensembles? They can be different neural networks. They can even be the same neural network with different initializations. Yeah, and they can be completely different topologies as well. The other thing that people have done here is to use something called specialists. And this was actually described in Hinton's paper in 2015 as well. And it was a way to convey the knowledge in not just one neural network, but multiple neural networks doing different things to a student network. And so what's happening here? They have this huge data set, which is growing every day, called JFT. I think it has 15,000 classes the last time I checked, but this always grows. And it has maybe 50 million images or something. And again, 300 million images. And again, that number keeps growing. You know, you follow their papers and they say, oh, we trained using JFT, which has 300 million images. And then they say 340 and then so on. So, so they have a huge data set. So what they do is that they actually have these specialists. So they divide their classes into, so they have 15,000 classes, let's say they divide it into 3. So they have each specialist kind of looking at just 5,000 of those classes. It's not being trained with the other classes, not doing anything with those. And then what they do is they have this extra step where they select the relevant output based on the correct class, and they minimize the divergence between, again, the output of the small neural network and the output of the specialist neural network. I think reading the paper will give you more details, and especially this box here, because they do, again, a fancy step there. But this is another way of having a very complex teacher network that is very difficult to deploy, especially on a mobile device or something. And then you can still use distillation to extract the knowledge from that larger set of neural networks into your student neural network. Yeah. Another thing is that so far we kind of talked about one distillation type. So basically the one we talked about is offline. So the teacher network has been trained offline, it's already pre-trained, and we just use its forward pass in getting some soft targets and then using that to train a student network, right? But I've seen some cases where you have online training of both the teacher network and the student network. And people sometimes refer to that as collaborative or mutual learning. And sometimes in that case, your teacher network is no longer kind of a big network and the other one is a small network. They're just two similar networks being trained collaboratively. And again, people have found that that can improve the accuracy a bit. And so people generally refer to this as online or collaborative learning. And another interesting one, which we actually used at Samsung when we were doing this stuff, is self-distillation. And this is also quite new. And so in some cases, you have a network that has multiple outputs. And in our case, the use case was quite simply, we want to train one neural network, but we want to deploy that one neural network to all Samsung mobile devices. And so you have your really good ones. I mean, this is an old picture, but you have your really good ones, you have your very kind of old and slow ones, but we don't want to maintain a model and deploy it differently for each device. We want to deploy the same software to all devices. So we train one neural network, and we have this concept of early exits. So for a very slow mobile device, we would just get the output of the first early exit, and we wouldn't run the rest of the neural network. For mid-range, we would go to early exit 2, and then for high end, we would do the final neural network output. And obviously, your accuracy kind of improves as you run more of the neural network. And so why is this relevant to distillation? We found that you can actually do self-distillation from the final output to one of the intermediate outputs. And so basically, you minimize the distance between the outputs of this final output, which is running the whole neural network, with the intermediate outputs as well. And we found that this improves the accuracy of the outputs, especially those early exits there. And so this was quite interesting, I thought. There are also different knowledge types. And so far, I kind of just said, let's use the soft targets, basically the softmax probabilities of a teacher network, but you can use other stuff. So typically, what we covered so far is called response-based. So it looks at the response of the neural network, and based on that response or output, it tries to distill some, uses that as knowledge and uses it in the distillation loss. But there's also feature-based. So in that case, instead of using the final output, and specifically the softmax of the final output, you can use the output of multiple layers and minimize the distance between multiple layers in the teacher network and the student network simultaneously. Or you can even look at the weights themselves and minimize the distance between the weights in a teacher network and the student network. More advanced versions of this is, you don't even just take the raw values of the weights in the teacher network and minimize the distance to the weights in the student network. You take kind of an attention map of the weights in the teacher network and minimize the distance to an attention map in a student network. And you do that throughout the network to kind of make it look more like the teacher network. And so what is this doing? It's trying to basically inject information into a student network throughout the network, not just at the final output, but in how the weights are structured, how the activation maps behave, and so on. So attention is a mechanism to focus on specific parts of the input or specific features. So basically telling the student network which parts to focus on and things like that. And so these are kind of more advanced loss functions. And usually kind of the loss function will start looking something like this, whereas here it was just kind of a distance function between the two outputs. Here it would be a distance function of a function of some feature of the teacher network and some feature of the student network. So it's still kind of a one-liner in some cases, but you need to kind of do more pre-processing in what goes in that one-liner. It's still kind of just an extra loss that you add. Finally, there's something called relation-based. I've never played around with this, but basically, instead of looking at just the output of a neural network or just the weights of the teacher and student neural network, or even just the attention maps of the weights of the teacher and student neural network, I'm taking pairs of layers here. So 2 layers from FT, which is the teacher neural network, and I'm computing some relationship between them. One of those functions is called a gramium between 2 features. And so I'm saying these 2 feature maps or these 2 parameter tensors should be related in some way that I don't know. I want that relationship to carry forward to the student network as well. So instead of operating on just one layer in the teacher and student network, now it's pairs of layers or even more. And so these are all kind of more advanced ways to extract knowledge from a teacher to a student. And you will find kind of lots of papers covering these specific cases. I will say this is still kind of the dominant thing, at least that we did in practice, and that has worked consistently across domains. When the loss function becomes more complex, like in speech and NLP domains, sometimes people go to feature-based or relation-based knowledge loss functions, distillation loss functions. So, okay, and then there are also a bunch of different distillation algorithms. So one of the readings for this week, I put this survey paper about distillation. Some survey papers are not good, but this one is actually okay. So it has a very thorough overview of all of the different variations of distillation. And here are some examples of what's in there. So we talked about multi-teacher a bit. We talked about attention-based, or basically getting those attention maps between the weights in each layer. A very interesting one is cross-modal knowledge distillation. So why is this interesting? So basically, let's say I want to train a neural network using heat maps, right? So the images are heat maps. And then I have a neural network trained on normal images, right? RGB. So usually we have way more RGB images than heat maps existing, right? So we have, ImageNet, for example, it's a data set with 1 million images, RGB images, and we have classification at the output. And so what people can do is that they take this teacher pre-trained on RGB images, which is a different modality or a different domain than heat maps, and then they take a small transfer set where they get the same images, and we no longer need 1 million images here. It could be 100,000 or something, or a small subset. We compute the heat maps for them, and then we find the distillation loss, right? So what I've done here, different than the image that we saw before in the slides, is that the input is no longer the same. This is a heat map and this is an RGB image. And I'm transferring knowledge from a teacher trained on RGB images to a student trained on heat maps. And so in this case, I can use knowledge that's pre-trained on something I have plenty of. And this is called cross-modal, basically, distillation. And I thought that was quite neat as well. Yeah. Let's say unsupervised training of a neural network. Data-free knowledge distillation just means you have a trained neural network and a student network, and instead of inputting a real image, you just input noise. Just input whatever, random values, and then use distillation to still transfer the output to the student. And your hope is that even if you put garbage here, then the output of the teacher will be meaningful in some way, and you want the student to copy the output of that teacher. So that's data-free knowledge distillation. People have used it successfully, but again, it's one of those niche kind of applications of distillation, I would say. Some people have also used distillation to train a quantized version of the same neural network, or to improve the accuracy of a quantized version. Yeah, and many other things in the paper that I recommend that you read. Yeah, and so here is the further reading. Please read it. And that's all I have for today. So if there are any questions, I'll hang around here for a bit and you can come up and ask.